I'm Naoyuki Hirasawa. Today I will present our paper, a flux-interpolated advection scheme for fluid simulation. This is collaborated work with Takashi Kanai at the University of Tokyo and Ryoichi Ando at National Institute of Informatics. Here is the outline of my presentation. First, I will introduce our motivation and related work. Second, I will describe our method, which consists of the new flux-interpolated advection method and correction methods for suppressing numerical diffusion and imposing cell volume incompressibility. Next, I will show experimental results. Finally, I will conclude our research and discuss future work. First, I will describe our background and motivation. Governing equations of incompressible and inviscid fluids consists of Euler equation, incompressible condition, and mass conservation equation. In the Euler equation and mass conservation equation, the advection term represents the movement of the quantities along with velocity. From now on, we will consider algorithms for the advection. The semi-Lagrangian method is the most popular advection method in computer graphics, which computes the method of characteristics on a computational grid. This figure represents the advection process of the semi-Lagrangian method. In the semi-Lagrangian method, we backtrace grid cell points by the velocity field and interpolate advected quantity. It is unconditionally stable and easy to implement. On the other hand, numerical diffusion occurs in most cases and violates conservation laws in the interpolation step. For these problems, several approaches extend the semi-Lagrangian method for reducing numerical diffusion. For example, high-order interpolation such as monotone cubic interpolation and Venn interpolation, the method of characteristics mapping for reducing the number of interpolations. Predictive correction by the McCormack method is proposed. Renting et al.'s advection method is also an extension of the semi-Lagrangian method. Their method achieves unconditionally stable conservative advection by renormalizing interpolation weights, but degrades interpolation accuracy and introduces numerical diffusion. Next, I will describe our new flux-interpolated advection method. Our novel advection method provides much conservation and improved numerical diffusion without resorting to higher-order interpolation schemes such as Venn 6. Now I will describe the overview of our method. Because the density advection and momentum advection can be calculated in the same manner, here I will discuss only the case of density. Our method is based on the semi-Lagrangian method, so what we should do is backtracing and interpolation. Unlike the conventional semi-Lagrangian method, we backtrace all cell boundaries instead of only a cell center. In this manner, density in a cell is denoted by a volume integral as the first line of equation. We further transform this volume integral to a surface integral over surfaces by Gauss's theorem as the second line. The integrand of this surface integral is characterized by the vector flux psi, whose divergence equals density. After the backtracing, we interpolate fluxes and evaluate surface integrals. The formulation by surface integral has an advantage for conservation of the advected value. Here we consider two adjacent grid cells like this figure. The total mass of these two cells is the sum of mass in the lower cell, given by the red surface integral. and the mass in the upper cell, given by the surface integral of the blue fluxes. Because the flux on the cell face shared by the two cells contracts regardless of the quadrature accuracy, the total mass in the two cells is given by the integral of the boundary of two cells. By applying the same arguments to the whole grid, the system's total mass is given by the surface integral of the grid boundary. So if the quadrature accuracy on the boundary is sufficiently high, the total mass is conserved. This is a basic principle of our proposed method. Next, I will describe each algorithm step. First, we convert density to flux. One-dimensional integral of the density is a flux, so we take the y-directional integral and define flux as the first equation. We can confirm the definition satisfies the property of the flux as the second equation. Second, we backtrace the vertices of grid cells and define cell faces by linear interpolation. Next, we build quadrature points on the grid faces. Also, our method satisfies the conservation law regardless of the quadrature accuracy in the bulk. We found that appropriate construction of the quadrature point is important to suppress visual artifacts. In our methods, we split each advected face by faces parallel to y direction and place one quadrature point per split face. We implement this split procedure by the matching square algorithm. After constructing quadrature points, we interpolate each flux on the quadrature point by the weighted sum of neighbor fluxes. A weighted sum gives the desired surface integrals and mass in the advected cell. To suppress numerical diffusion and impose cell volume incompressibility, we also introduced two correction methods. I will describe these two correction methods in the following slides. The first correction method is the predictive correction of the numerical diffusion. In our framework, we define mass in a cell by surface integral. So finite support of the linear interpolation introduces the numerical diffusion. If we adopt piecewise constant interpolation, no numerical diffusion occurs when the velocity is zero. But aliases occur due to the discontinuity of the interpolation. We estimate the errors by the difference between linear interpolation and piecewise constant interpolation. We then correct advected values to reduce diffusion. The second correction method is a cell volume correction by artificial pressure. Ideally, incompressible fluids preserve local cell volumes. However, due to the interpolation errors, advected cell volumes do not preserve cell volumes in general. To impose incompressibility of cell volumes, we introduce artificial pressure force and shrink or expand cells by the artificial pressure gradient. Next, I will show experimental results. The first example is two Smoky spheres collision. Our method is upper left. Our method achieves much more mass conservation compared with the McCormack method of characteristics, and semi-Lagrangian method. Renting et al.'s method also conserves the total mass, but our method improves numerical diffusion at the same time. We experimented with another scene, one-way coupled smoke simulation. Like the previous scene, our method achieves much more mass conservation and improved numerical diffusion without high-order interpolation such as Ueno 6. To compare numerical diffusion with Renting et al.'s method, we provide 2D disk rotation experiment. As seen in the results, our method is less diffusive than Renting et al.'s method and preserves high-frequency features. The Taylor-Green vortex experiment shows the effectiveness of the cell volume correction. We initialize density uniformly and set velocity to incompressible Taylor-Green vortex. Due to the incompressibility of the velocity field, density should not be changed from the initial time. This result shows that density remains unchanged in our method with cell volume correction, but leads to condensation artifact without cell volume correction. Our method also can be applied to the momentum advection. Here is the results. We found that the momentum-preserving advection generates visually different motions. However, we did not observe clear improvements in visual quality. Since our method for momentum advection is 3 times more costly than mass advection, we found that our method is not cost-effective, at least for smoke simulation. This situation may differ for liquid as demonstrated in Lentin et al.'s work. We conclude our presentation and discuss future work. To summarize our research, we proposed a new flux-interpolated advection method for fluid simulation that shows high conservation and improved numerical diffusion. As future work, we found that our method is sensitive to floating point errors, so we would like to reduce these errors. Our method induces unphysical negative mass inevitably. We can't observe any artifacts in the smoke scenes with ray tracing rendering, but other scenes such as liquid are not studied. We implemented only linear flux interpolation. Extensions to high-order interpolation, such as cubic or Venn interpolation, may further reduce numerical diffusion. Thank you for your attention.